Okay, this is going to do it for Chapter 18. We'll wrap up this hell of a chapter with a little bit of a wrap up on the aldol and some synthesis stuff. So, when last we left you, we had just talked about that mess that is crossed aldols that we have now learned that you can control by judicious choice of conditions. But you need to be aware that if you mix aldehydes and ketones up with different structures, you have the possibility for a messy mixture of products. Now we're going to look at some additional examples of aldols, the intramolecular versions, the Robinson annulation, and then just look at some synthetic stuff. So intramolecular aldol reactions. Remember that intramolecular reactions are reactions where the electrophile and the nucleophile are all part of the same molecule. Intermolecular is like interstate highways in between two molecules. The reaction takes place with a nucleophile from one molecule and an electrophile from a different molecule. Well, intramolecular is always favored well over intermolecular if you're making a 5 or a 6-membered ring. So in the textbook it goes through the example of 6-oxoheptanal, and I just want to point out that that's a typo, that there shouldn't be a dash right there as the book suggests. But moving along, some helpful hints on how to deal with these intramolecular aldol reactions. First, you want to look at all the possible alpha hydrogens. If you identify the alpha hydrogens, you know what the potential enolate nucleophiles are. So, for example, in this molecule, we've got alpha hydrogens here and alpha hydrogens here. So we could have an enolate forming here or an enolate forming here. Okay, so two possibilities. Then just count. Can any of those potential nucleophiles react within the same molecule to form a 5 or 6-membered ring? So if this is carbon 1, 2, 3, 4, 5, 6, sure enough, it could react over here to make 1, 2, 3, 4, 5, 6, a 6-membered ring. Similarly, this guy, if there was a nucleophile here, it could react over here to make a 1, 2, 3, 4, 5, 6-membered ring. So it looks like we've got two favorable aldol possibilities here. Well, then we have to think, well, which one is going to be favored if one is more favorable than the other? The example we looked at in class and the example we looked that they present in the book, there is a favored outcome, because in that example there was an aldehyde and a ketone, and we found out that basically the aldehyde electrophile is more reactive, and so that is the ultimate product. So let's look at this one in a little bit more detail and show how you can figure out the product as long as you pay close attention to what you're doing. So here it is. We're going to start out as usual by crossing out our spectator ion. We're under basic conditions, obviously, and so we will arbitrarily choose to deprotonate one of the alpha hydrogens. And I'm just going to pick that guy off. That gives me this enolate. And we have decided that it can react intramolecularly with this electrophile to give you, again, a 1, 2, 3, 4, 5, 6-membered ring. So I'm going to go ahead and number these. You'll notice that this numbering doesn't have anything to do with nomenclature. It is just for me to see who is connected to who. So, again, I should point out that these are all reversible reactions. So I'm making a 6-membered ring, so I can just put up my 6 carbons here If I could count, I could. Okay, kind of a pathetic excuse for a hexagon, but it'll just have to do. Okay, and then I know that they're going to be connected in order. So, carbon 1 was my enolate carbon, so it is connected to the aldehyde group and a hydrogen. Carbons 2 and 3 were both CH2s. Carbon 4 has that methyl group on it. Now, is it R or S? Looks to me like this would be the highest priority, second priority. That looks like S to me. So if I put the H in the back, is this S? Oh my God. Well, we'll assume it is for right now. I don't want this to last 30 minutes. Okay, but it should be S. Okay. Carbon 5, another CH2. Carbon 6 was where it attacked, so we've got our O minus and our hydrogen. Okie-dokie. Now what? Well, it's an aldol, so we know we're going to end up protonating the oxyanion to give this as my product. And we should say something about the stereochemistry. We didn't muck around at all with the stereochemistry at this stereocenter, so it stays the same. But here, these two stereocenters, well, they'll be both R and S, but it's way beyond the scope of this class to try and predict how much of each you'll have. Just stand forewarned that you'll have a mixture of stereoisomers. Okay, so that's fine and dandy. What would have happened if I had deprotonated at this site? Well, then we have this nucleophile reacting with this electrophile. Same exact mechanism. We'll number our carbons again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's a little better. If this is carbon 1, 2, 3, 4, 5, 6. Carbon 1 has the aldehyde. Carbon 2 has the methyl group. 3 CH2, 4 CH2, 5 CH2, 6. So our product upon protonation is this guy. And you can see that they are definitely different, completely different isomers. They both have that classic 1, 2, 3 relationship that shows that it's an aldol. And so if I wanted to make, say, this molecule by an aldol from this particular starting material, it'd be a pretty bad deal because I'm going to get a pretty darn close to a 50-50 mixture of this isomer and this isomer because there's nothing favoring one over the other. You know, it's not going to be exactly 50-50, but it's not going to be a pretty sight. So, that's an example of an intramolecular aldol reaction that doesn't work very well. So now we move on to the Robinson annulation. Nobel Prize winning chemistry by this handsome dude. This is Sir Robert Robinson, kind of a big kingpin in organic synthesis. The Robinson annulation is pretty cool because it's a combination of two reactions, the Michael reaction and the aldol, to build in one swell FOUP a cyclohexenone. So the Michael reaction, you, I hope, recall, is when you're adding an enolate 1,4 to a conjugated system. Okay? Soft nucleophile, soft electrophile, right there, gives you, ultimately, that product via this intermediate. Okay, so that enolate comes back down again and it gets protonated. That's not usually under acidic conditions, so negative charge swings down, picks up the hydrogen, and there's your product. The Michael reaction product invariably has a 1,5 relationship of carbonyls. So what Sir Robert figured out is that if you put these two together, you get some pretty spiffy chemistry. So if we took this Michael product and then treated it to conditions that allow an aldol to take place, well, I get an enolate here, 1, 2, 3, 4, 5, 6. Aha! That'll give me a reasonable intramolecular product. If my enolate forms here, 1, 2, 3, 4, that is definitely disfavored. If my enolate forms here, 1, 2, 3, 4, no way a four-membered ring is going to happen. But the enolate here forms an easy access to the aldol product. Aldol product then is dehydrated, and there is your cyclohexenone. So it's a very cool way of putting together two pieces to make a six-membered ring. And six-membered rings are very common in natural products in nature, and this was a huge, huge feat for humanoids to be able to make these kinds of skeletal structures. What's really cool is that some people are brilliant enough to be able to look at a product that has a cyclohexenone in it, like this guy, and figure out how to make it using the Robinson annulation. So, how could we make this using this chemistry? Well, it's not as hard as it seems. We know that it's this alpha-beta unsaturated skeleton that is telling us aldol, aldol. And sure enough, if we would just dehydrate across these two carbons, we'll get that double bond. Okay? And now we can certainly see that this is an aldol product. So it means just retrosynthetic stuff some more. How can I make this by an aldol? Well, sure. Remember the alcohol disconnection. We're going to push those electrons back in and break this bond to regenerate the carbonyl here and end up putting an enolate right there. And sure enough, that's exactly what we're pointing out, that if I can just generate this enolate, it will do an intramolecular aldol reaction to give this product. 1, 2, 3, 4, 5, 6. Okay, so how do I make this? Okay, so right here, let's kind of spell things out. This was just the dehydration. This was the aldol step. So we need to keep going backwards to the Michael reaction. So looking at this over here, we see the 1, 2, 3, 4, 5 relationship between the two carbonyls. That is telling us this is a Michael reaction. So if I do a disconnection right here, I can break this up into a reasonable nucleophile and a reasonable electrophile that would react together to make ultimately that product. So in the very end analysis, we're starting with hexanone and deprotonating it. Selectively, we have to make the kinetic enolate. So we'll use some really strong base that it will deprotonate the more available alpha hydrogen. We'll probably do this in the cold, so it's like a common cold temperature is minus 78 degrees because you can easily achieve that in the lab with dry ice. So deprotonation of hexanone with lithium diisopropylamide under cold temperatures will allow me to pretty specifically generate the kinetic enolate, which can then be added to this cyclohexenone, and that gets me to here, to here, to here. So this is being able to think backwards like this is really a long-term goal for you guys. We're going to start with baby steps. We've been starting with one step backwards. By the end of the semester, you too will be able to do this. You won't see any of these hairy retrosyntheses on the exam, but you most likely will see it on a take-home part of the exam or homework. I haven't quite decided yet what's going to be happening with that. So know that, yeah, some simple synthesis will be on the exam, but nothing as complex as the one that's on this slide. Okay, so let's look at some simple quote-unquote synthesis and realize that the key, if you haven't figured it out already, is to focus on that target and think, now how can I make that in one step? So you'll do the disconnection so that you're pulling this target molecule, this big complex target molecule, apart from a big carbon thing to smaller pieces that have an electrophilic piece and a nucleophilic piece that will react to get together to give you your target. So some screaming bells and whistles in this chapter. As we've already said, for the aldol, the alpha-beta unsaturated carbonyl system is screaming aldol, as does that 1,3 aldol relationship. So aldol city man, aldol, 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 scream, scream, scream. Okay, so use that alcohol disconnection. Push the lone pair from the oxygen back in. Make your selective enolate here. Here's your electrophile. There's another screaming bell and whistle in this chapter, and that's the Michael. So when I see this target and I recognize that this is a 1, 2, 3, 4, 5 dicarbonyl, I know I can make that in a heartbeat from a Michael reaction. So that means one of these has to be an enolate and the other has to be an electrophile. And sure enough, if I take this ketone, deprotonate it, and add it to this alpha-beta unsaturated carbonyl, then I'll get this product. Here's a question for you. Given this target, there's more than one way you can make that target by a Michael reaction. So, can Can you think of the different Michael disconnection? So those are the simple ones. I gave you a tough one on the worksheet from Wednesday, the 19th. Here is another example. Here's a target. There's no obvious 1,3, there's no obvious 1,5, there's no alpha-beta unsaturated carbonyl. All of the hints and bells and whistles are gone. So you just have to work backwards one step at a time and recognize I know how to make an imine from a carbonyl. I know how to make a ketal from the reaction of a ketone with an alcohol. I know how to make a diol because it's got that 1,2 relationship. That probably came from an alkene or, oh yeah, sure, I know. If I add hydroxide nucleophile to the selectrophile, I'll get the diol. And how do I make an epoxide? Well, I know how to make an epoxide. I make an epoxide from the alkene. So, think backwards, you know that. And more importantly, one step at a time. And you'll notice I didn't say anything about starting material. You don't even want to think about the starting material. Just work backwards doing chemistry that you've seen before that breaks down into reasonable nucleophiles and electrophiles. Okay, so we're going to wrap it up completely with just a really bad, you would expect nothing more, really bad North Dakota joke. So, where is the North Dakota joke that I was going to... Oh, yeah. Two North Dakotans go into a bar, and they buy drinks for everybody in the place. They are celebrating and whooping it up, slapping everybody on the back. So the bartender says, well, what are you whooping it up for? What's the occasion? Well, they said, we just finished a jigsaw puzzle, and it only took us 2 months. The bartender says, 2 months? What's the big deal? It shouldn't take that long to do a jigsaw puzzle. Oh, yeah? Says one of the North Dakotans. On the box it said 2 to 4 years. Yeah, you gotta love it. I sure hope none of you are from North Dakota. But that's all for Chapter 18. We're going to do lots of problems. More practice than you can shake a stick at, and we'll see you in class.